Welcome, folks. Still going to be another 5 minutes or so before we get started with the lesson. Just wanted to get the stream up so I could make the classroom post. All right, folks, can you hear that better now? My apologies. All right. So please type a 1 in the chat if you can hear me now. My apologies for not getting that figured out. I'm impressed that you're still here, actually. Oh, good. All right. Sorry about that. Okay. So we're talking about well, actually, let me do some of the intro again, because there's a few things there that you need to know. So the first one is, or really the main thing that you need to know from the intro is that there's a summer school upgrade course available for students who would like to improve or reinforce their math knowledge. So it's for the whole Waterloo Region District School Board. They'll make as many classes as they need based on the number of students. And there's one of these courses for every grade 11 and grade 12 math course, I believe. But in particular, there's one for advanced functions. So if you feel like you want to improve or reinforce your knowledge from this course, get in touch with your guidance counselor and you can sign up for that. Okay, so we're dealing with the Richter scale, which is for measuring earthquakes. And as with many of these logarithm word problems, there's a variable that is a reference intensity, I naught, that's part of the equation. And usually we won't know what number I naught is, but we'll often be able to get it to cancel out of an equation. So when we're doing solving, we'll usually end up with two variables left, I and I naught, or maybe M and I naught. But as we continue to work, we'll be able to cancel out I naught. So don't be worried if at first you're like, hey, wait a minute, how am I going to solve this? There's two variables left I don't have numbers for. Usually that we'll get a cancellation there. So this is the formula for the Richter scale for measuring earthquakes. We take the intensity of the earthquake divided by the reference intensity, take the log of that, and that is our Richter scale rating. So in 1989, there was an earthquake in San Francisco, and it measured 6.9 on the Richter scale. And in 1964, there was an earthquake in Alaska that measured 8.5 on the Richter scale. So the first question in the handout 3.17.h that's up in the classroom asks how many times as intense as the San Francisco earthquake was the Alaska earthquake. So in other words, we're looking for the intensity of the Alaska earthquake divided by the intensity of the San Francisco earthquake. All right. Okay, give me a 1 in chat if that's making sense so far before we dive into the algebra. Great. Thank you, Daniela. Thank you, Caitlin and Ramesa. Okay. So San Francisco, the Richter rating is 6.9, and that is equal to log of I over I naught. And here you can see what I was talking about earlier, where there's two variables whose values we don't know. In Alaska, so I guess I should say this is San Francisco intensity. For the Alaska earthquake, we have 8.5 as the Richter rating, and that is equal to the log of the intensity of the Alaska earthquake divided by the intensity of the reference quake. All right. So we've set up both equations, and what we're looking for is I Alaska divided by I San Francisco. So with both of those things stuck inside logarithms, that's going to be difficult. So I'm going to change this to exponential form. When the base isn't noted, we're base 10 for logarithms. So 10 to the power of 6.9 equals the intensity of the San Francisco earthquake divided by the reference intensity. And we can do the same thing over here. 10 to the power of 8.5 equals intensity of the Alaskan earthquake divided by the reference intensity. So, okay, how do we get intensity of Alaska divided by intensity of San Francisco? Well, I can do ISF over I naught, all divided by I Alaska over I naught. That's probably not the cleanest way to do this, but hopefully it will make some sense. And, oh, sorry, I should do it the other way around. So Alaska on the top, San Francisco on the bottom. So that means I'm going to get this, we know from this equation, is 10 to the power of 8.5. This one we know from here is 10 to the power of 6.9. And we know, going back to grade 9 with our exponent rules, that if we have a division of two powers with the same base, we can just subtract the exponents. And that is 1.6 as the exponent. These two areas here, though, if I multiply top and bottom by I naught, I'm going to get some nice canceling, and I'll end up with the intensity of Alaska divided by the intensity of San Francisco. And that is 10 to the power of 1.6. And we can plug that into a calculator. 10 to the power of 1.6 equals 39.8. So you can see here that although their Richter scale difference is pretty small, it's 1.6, their intensity difference is quite large, it's 40. And if we picked, instead of a 6.9 earthquake, we picked like a 3.9 earthquake, then we would get a really much larger number here for the difference in intensities. And that's one of the useful things about log scales, is that they allow us to compare vastly different intensities in a reasonable way with numbers of similar sizes. All right, give me a 1 in the chat if that's making sense so far. And if you have questions, as always, please ask them. Great. Okay, thank you. So part 2 of the question asks us, so this was part A. Part B asks us to calculate the magnitude of an earthquake whose intensity is twice as intense as the San Francisco earthquake. So the intensity is 2 times the San Francisco earthquake's intensity. There we go. All right. So we're going to deal with this in taking advantage of logarithms. So we have magnitude equals log of 2 times the intensity of the San Francisco earthquake divided by the reference intensity. We know from our logarithm laws that we can do, if we have a multiplication, we can make that into a sum of logarithms. So we have m equals log base 10 of 2 plus log base 10 of the intensity of the San Francisco quake divided by the reference intensity. And so you might ask, okay, why did you do that? Why would you separate it that way? Well, log of the intensity of the San Francisco earthquake divided by the reference intensity, this term right here, that is the formula for getting the Richter value or the magnitude for the San Francisco earthquake. And we know that, right? We were told in the question that the magnitude for San Francisco is 6.9. So here I know that this is log base 2 plus 6.9. And now I can finish the calculation on log base 10 of 2 plus 6.9. And so we get 7.2 approximately. All right, so by using my log laws, I could split this up into something that's purely numerical and I can calculate, and something whose value I already know, and then that gets me to an answer. So therefore, an earthquake with twice the intensity of San Francisco has magnitude 7.2. All right. Okay, so give me a 1 in chat if that's making sense. And if you have a question, feel free to jump in and ask it. Thank you, Daniela. Thank you, Caitlin. All right, so I'm going to give Rumesa a moment to ask a question. In a moment, we're going to move down to the next page of the handout where it's talking about the decibel scale. Thank you, Rumesa. All right, so then let's look at the next page here. We're talking about decibel scale. So this is for measuring sound. Uh, One of the really neat functions of the human body is how our ears measure or how our ears receive sound. And in particular, sound waves can range from very, very quiet to very, very loud. And we experience them as being sort of within some reasonable range, right? Like the volume on most electronics might go from 1 to 10 or 1 to 100. But the intensity, the energy in a sound wave actually is a much larger range of intensities. So, and we'll see that here, but basically every 10 decibels a sound goes up, it multiplies itself by 10. So 10 decibels sound is like the quietest thing we can hear. 120 decibel sound is like almost ear, like causing, it's definitely causing hearing loss. And up to like 130, I think, is about a jet engine. So the difference between 10 and 110 is 10 to the 10. In other words, a 1 followed by 10 zeros in intensity. So it's really a massive range of intensities that our ears can comfortably deal with. And the way the ear is built is a really neat thing that allows it to do that. So if you have some time, you can check that out. Let's deal with the math. So we see that the log equation is very similar, except this time we have a 10 out front. It looks a lot like magnitude for earthquakes, slightly different. So our sample problem, a sound is 1,000 times more intense than a sound you can just hear. What is the measure of its loudness in decibels? So a sound we can just hear has an intensity of I naught. Right? And so you can see that in the right up there. Its intensity is going to be I naught. So the reference intensity here, we don't know its value in terms of energy or pressure of the wave or anything like that, but we know that I naught is a sound that a human can just barely hear. So we want a sound that is 1,000 times that, and we want to know what is its decibel reading, so L for loudness. And we know that the intensity of this sound is 1,000 times a sound we can just hear, which is I naught. So we plug this into the equation. 10 equals, not 10 equals 10 log of our intensity, which is 1,000 I naught, divided by the reference intensity. And so again, you might be looking at this going, wait a minute, we have a lot of variables here. How am I going to solve this? Well, I naught and I naught cancel out. And so we get 10 log base 10 of 1,000. And that's easy to solve. Log base 10 of 1,000 is 3, because 10 to the 3 is 1,000. 3 times 10 is 30. So the loudness in decibels, 30 decibels is the sound that is 1,000 times louder than a sound you can just hear. Or 1,000 times more intense, I should say. Sound that is 1,000 times more intense then you can just hear is 30 decibels. All right. So give me a 2 in chat this time if that's making sense. And if you do have questions, feel free to dive in and ask them. Thank you, Daniela. Thanks, Caitlin. Thank you, Ramisa. All right. So let's move to our last example here. So this time we're talking about a third scale, the pH scale. And so if you scroll down to the next page in the handout there, pH scale, as you probably know from science class, goes from 1 to 14. A high pH above 7 is acidic, and the higher it goes, the more acidic. A low pH is basic, and the lower it goes, the more basic. You don't really want to put your hand into either high pH or low pH. Around 7, that's neutral. So regular water, pure water, has pH of 7 exactly. Okay. So we have a formula here. The pH of a substance is calculated by taking the negative log of the concentration of hydrogen plus ions. So in other words, these are just free protons because the hydrogen atom only has one proton, one electron normally. And so if it's positive, it's lost that one electron, and it's just a proton floating around, maybe with a neutron, but most of the time hydrogen doesn't have neutrons. Okay, and you'll note that H plus, we measure that in moles per liter. In moles per liter. And if you don't know what moles are, that's all right. You can think of them like dozens. They just count things, but they're a much bigger number. Dozen is just 12. Moles is like massive, massive number. Okay. So our sample problem here, find the pH of a swimming pool with a hydrogen concentration of 6.1 times 10 to the negative 8 moles per liter. So we set up our equation, negative log, and the information we have is this hydrogen concentration, which is going to be 6.1 times 10 to the negative 8 moles per liter. And here we can just go ahead and calculate straight up. This is probably the easiest of the questions that we're looking at. So we go negative log 6.1 times 10 to the power of negative 8. And we get that it is 7.21, etc. So swimming pool concentration, or swimming pool pH, pardon me, is about 7.2. And that kind of makes sense, right? A swimming pool is mostly filled with water, so we would expect its pH to be somewhere around 7 because that's pure water. But obviously, it's not pure water. It's got chlorine in it, and that's going to change the pH a little bit. All right. Part B or part 2 here, we have pH of a fruit juice. We know it's 3.1. And we want to know what the hydrogen atom concentration is. So again, we're going to set up the equation here. Oh, sorry, camera is blurry. Low is acidic, pH, high is basic. Thank you, Ramisa. Okay. So hopefully folks can see this. I'm looking at it now and it looks like it's reasonable. So if there's any problem, please do let me know. I'll try to stay watching the stream now instead of going back to the question. Okay, so we have a pH of 3.1. We want to know the concentration of hydrogen atoms. So we again use our equation, negative log of hydrogen atoms. And we're going to turn this into the exponential form. So I'm going to move the negative sign over in front of the 3.1 and then change this to exponential form. And so here we can see that we get 10 to the power of negative 3.1 is equal to the concentration of hydrogen atoms. And if we calculate that, 10 to the power of negative 3.1, we get that the concentration of hydrogen atoms is 0.000794, which is equal to 7.94 times 10 to the negative 1, negative 2, negative 3, negative 4. All right. So let me know what questions you have about that, or give me a 1 in chat if that is making sense. Thank you, Caitlin. Thanks, Ramesa. Daniela, did you have a question about it? Cool. All right. So that is it for the lesson for today. Homework is to do questions 1 through 4 on page 4 of that handout. The solutions are given below, so you can check your answers and make sure that you're on the right track as you go. If you do have any questions, please feel free to send them my way. And as always, have yourselves a great day. We'll see you again on Friday.